So I'm going to talk to you about the hermit in the tree. In fact, I'm going to talk to you about 2 hermits and 3 trees, so let's spot them during the talk. And please interrupt and ask questions as I go along, except questions about the topic. Okay, so I start with a bit of motivation, and as you all know, often when you're writing a programme you get this trade-off between the clarity of the programme and the efficiency of your language. And often it would be nice if you could just transform a clear programme into an efficient one, either taking the programme you've already got and optimising it, or taking the specification and providing an implementation of that specification. What we're interested in, the work we've been doing, is about mechanising this sort of programme transformation in the context of Haskell programs. And I want to do this mechanically, and that's what I'm stressing here, because while you can do some pen and paper reasoning to prove two programs equivalent, this is usually more time-consuming and error-prone. And if you have a mechanical transformation, then you can just have your Haskell source file and you can just mechanically transform it. There's no chance of manual errors being transferred. Okay. So there's been quite a bit of work being said on Haskell, various other transformation systems, Haskell programs, here's a few of them. But all these systems that I'm aware of, at least, all operate on Haskell source code or some variant thereof. Now, you might wonder about my inclusion of but in this sentence, because it's not what I just said I wanted to do on the Haskell program. So my concern here is what we mean by source code. Right? So what is Haskell source code? Is it Haskell 98? Is it Haskell 2010? Is it Haskell with those GHC extensions? I would guess that most people use very different versions of Haskell depending on what they're doing. If you are using extensions, which extensions are you using? And it's hard to keep up with all the new GHC extensions because new extensions keep coming out all the time. And all these information systems are quite limited in terms of not being able to cope with the latest extensions or the latest syntax. So we decided to take an alternative approach and work on GHC core, which has been nicely introduced by previous talks, which is GHC's intermediate language. And I'll give you a quick glimpse of what it looks like. You don't need to memorise all that if you don't know it already, it's just to give you an idea. So we have expressions, applications, abstractions, and lets, cases, and a few other things. But the main point about GHC core language is it's a lot smaller and simpler than GHC's, Haskell's circuit syntax. A lot of syntactic flutters gone, the rest of it being simplified. And we also have type information there. Okay. So we're going to be interested in transforming programs in this language. So that's the abstract syntax tree that is referred to in the title. So I should also explain what is HERMIT. So HERMIT stands for Haskell Equational Reasoning Model to Implementation Tunnel, which is quite a mouthful, which is why we just say HERMIT all the time. And in one sentence, it can be described as a toolkit for transforming GHC core programs. We're developing this in a team in Kansas, in the town of Lawrence, which is perhaps unfortunate because we might get confused with this guy here, who's a celebrity, also from Lawrence, but he's nothing to do with us. I realise he looks like a hard programmer, but as far as I'm aware, he wasn't. But he beats us on Google. Okay, so HERMIT, it's a toolkit. It's been released as a package on package as of about 5 days ago. If you've got GHC 7.4, you can download it and run it right now, hopefully. If you try downloading it and you can't run it, please talk to me and I'll try and solve that. I'm trying to make it as easy as possible to use, so you just install it with Caval and then you just run it on your top-level Haskell file. And this HERMIT command just invokes GHC with a bunch of default flags that we find useful. Most of which you don't actually need, we just find the important thing is this plugin equals HERMIT here, which means we're using the recent GHC plugins mechanism, which lets us interact with the GHC compiler midway through compilation, drawing the simplification and optimization phases and active filing constellations. Okay, so I'm going to give you a quick demo now before I talk about any more, just to give you an idea of what HERMIT is and how it works. So here's the classic Fibonacci function, all know and probably doing this week. I'm going to show a very simple transformation on this function. Okay, so what I'm going to do is unroll the recursive calls for fib, okay, to make it look like this. So it's not a very interesting transformation. It actually speeds up Fibonacci a little bit because there's less function calls. But it's not really very interesting, but it serves as a basic demonstration. So let me just show you the source code just to convince you there's no magic happening here. There's no funny trickery. It's just an plain Haskell source file. What I'm going to do is load that up inside the HERMIT system. So, and I'll just invoke GHC. GHC starts running, and then it will pause midway through compilation. This is before any optimizations have been applied, but after type check. Okay? And what we have here is via our fitting printer a view of our module. Okay? So we've got a main module, we've got a fib function, we've got a main function. In fact, we get two main functions. That's just some funny GHC. Which is something I have to say a lot about. So I want to look at the fib function. So I tell HERMIT I want to have a look at it. Consider it command. And now we zoom in and have a look at the fib function. And this is what fib looks like inside GHC core. Okay? So you can see it's roughly the same, but there's been a few changes. So pattern matching, which we call nested case statements. For example, the infix operator has been placed in the prefix position. Yes?
The nitty details, but why is that tick?
Alright, so this is just our notation. We've stolen this from template Haskell. We use a tick in front of something if it's a variable in the source code. If it's an actual recognized HERMIT command, we don't have a tick. But it's just a naming convention.
And this is showing core?
Yeah, that's showing GHC core.
Without types?
It is showing it with types, it's just in this function.
Yeah, there's just no type
types.
there.
I'll come back to that point later on. I'll actually show you some types at the end. We have different treating printers depending on how you want to display your type information. So the transformation I said I wanted to do is inline those two calls of fib. Now, as got mentioned in the previous talk, you've got to be careful when inlining recursive functions because it could inline forever. So I'm aware of that, however, so I'm going to tell HERMIT I want to inline fib using a traversal strategy which we call n bottom up. So BU stands for bottom up, that's a post order traversal, I think. So start at the leaves of the tree, working our way up, and anywhere we see fib, we're going to inline it. Okay? I don't want to do this in a top-down manner because it goes down. So now you're going to see a nice splurge of code now, which you probably won't be able to read, but maybe you'll roughly see that we've got an inline definition of fib here, and we've got an inline definition of fib here. It's getting a bit ugly at this point. So I'll demo some more interesting things later on, but for now I'm just going to say first with GHC you now do its compilation. So I'll just say resume, which gives this code back to GHC, and GHC carries on and will compile it. And now you've got environment as usual. So yeah, I'll have some more interesting demo later. Let's get back to my talk for now. So HERMIT provides a variety of different types of commands. Here's just a few examples in various categories. So we have a lot of rewrites specific to the GHC core language, so need to be done to for expansion. The sort of case manipulations that we saw in some early talks this morning would provide that sort of thing. We also have these higher level traversal combinators which come from a strategic program library called Gill. And that provides these traversal strategies such as the NEBU, which shows you that the traversal poetry applies everywhere. There's also strategies for repeating rewrites until they can no longer change anything. various fixed point reversals and such like. We have navigation commands for just wandering around the tree, so you can navigate to where you want to go. You can either do very basic, sort of up-down commands, or you can say you want to consider a specific point, and you can navigate down to different children. We also have a version control system for your fragment of GHC4, so you can modify it and then backtrack if you decide that transformation is actually a mistake. You can build a version control tree. And you can save any transformations you've applied as a script, which you can allow in the future. And indeed, you can just run a script with it, and you don't have to automatically go to it. Okay, so here's a picture of our sort of development methodology. The idea is, the user of HERMIT, there's a load of transformations already provided. We've got about 100 so far. It's in our library. And you sit down and do a sort of interactive session I briefly showed you earlier, where you try out transformations, you move around the tree, you experiment. And once you've found the transformation you want, you write it as a script, and then you might go back interactively, load that script and apply it in certain places, and you just keep experimenting until you're happy, and then you try and capture that abstraction and then encode it in this pure language, which is a more strongly typesetting. And what you capture the abstraction exactly as you want it. You add it to your dictionary of transformations as something available for everyone else. We're at the moment just going around this circuit, just developing new transformations and trying to find higher level abstractions. Okay, so the particular paper that's in the IFL proceedings, we've been experimenting with taking HERMIT and using it to mechanically apply a variety of established program transformations from the literature. So we took these three transformation techniques, and we, well, so far successfully encoded a selection of examples from each one, which you can find in the code and actually discussed in the paper. I'm not going to talk about what these transformation techniques are, they will follow on to HERMIT talking about. Only in the process we did discover that the top two can be cast as instances of the bottom one, which was interesting. It certainly made our work a lot easier. It turned out our work around the transformations we encoded proved reusable. So I want to give you a more interesting demonstration of HERMIT work now. So here's the Fibonacci function again. Here's a more interesting transformation of Fibonacci, and that's converting it from the naive exponential time definition to this linear time definition that just returns a tuple. So that's two adjacent Fibonacci numbers and doesn't have all the duplicated work. I'm going to assume you're familiar with this transformation. So to encode this transformation, I'm going to use the worker-appler framework established. Now, if you're not familiar with the worker-appler transformation, you have to define these additional conversion functions to go with it, a wrap and an unwrap function, which are generally small, simple things. But you have to, according to the way HERMIT's set up at the moment, you have to do these in your source code. So here's what my sort of modified source code is going to look like. I've got some additional functions, wrap and unwrap, that I'm going to use as part of the equation reasoning. I've also used the GHC rules applying that I mentioned earlier to encode some rewrite rules. So HERMIT exploits this rules primer quite a lot. So if you as a user have some rule you want to be able to apply inside the HERMIT system that HERMIT doesn't provide already, or that because they're specific to your function to a user, you can just encode them as a rule and we make them available to the HERMIT user. This also means if you're a rules user, you're not really interested in HERMIT per se, you use HERMIT to test out your rules and debug them and apply them when you expect them to. We find that's quite convenient to be able to interactively test them out and see what's happening. So before I start transforming, let's have a look at how long Fibonacci takes to run before transformation. So Fibonacci here is taking 0.23 seconds. Remember that figure. call again, this time with this graphical function lying around. And now I've already done this example, so I've got transformation script pre-written. This is what it looks like. So this performs the worker wrapper style derivation of the efficient version of the anarchy. Now, I'm not going to go through the whole thing because that would take far too long. So, I'm just going to show you the basic fib code again. So, we starting off with the normal definition of fib, then just as we had before. Let's go back to where we were. Now, I'm going to load that transformation script. Loaded the 39 commands there, it's applied them all. All this code is available on the web page. You can see that and try this out and see what's happening. You can see this all works under the walkthrough in the paper itself. But now I've produced the efficient version of what we're looking for. So you had a question earlier about types. So at the moment I've turned off types. You can see at the top of the file here I said emit. And this is a command to tell HERMIT not to display types because they're not overly relevant for this example. But you can also show the types. So here you can see that these tuples take match with its type argument.
And your transformations are always typed.
Sorry?
The transformations are always typed, so...
Yes. And what we have is the default setting is we make typed abstract. Because we usually want to remember they're there, but they're usually not immediately relevant. So we just type them. And you can just do whatever you want. Okay, so now let's give this back to GHC and see if this has worked. So before it was 0.23 seconds, I think. If we do it now, it's 0.6 seconds. That's 0.06 seconds. So it's not that. Okay, so that's what we're all to say today. We're building this transformation tool to allow it to interactively transform your core programs. This paper is about our experiences of mechanizing some existing transformation techniques. We also have another paper in the Haskell Symposium which talks more about the implementation of the HERMIT system. We're interested in that. And our plan for future work is to take the transformation we've got and build a proper equational reasoning framework. So at the moment we allow transformations to go to the correctness. To start with, using GHC rules, previously discussed, you can just put in the GHC rule that changes the meaning, things like that. We want to build a more descriptive framework how to get some correctness guarantees about the transformation. Questions?
Other questions?
So what I really like about this is that you can take your program and then instead of kind of staring at the core, you have a bit more automation to be able to optimize your program in certain ways. But if you still look at, suppose you have some program transformation in mind, like say the worker wrapper transformation, it still seems that you need to do quite a lot of work in order to teach HERMIT how to apply the worker transformation to this particular example that you have.
Yeah, so this is not aimed at transformations that do require some user guidance. The can't be optimized with sort of automated with a compiler.
Yeah.
So transformations either in general aren't true, but only true in a specific instance, or wouldn't necessarily in general improve performance, but you know that in your specific case they would. And the aim is, so the moment you have to write a script and load it to it, we would like you to be able to just have that annotation in the Haskell source file like a GHC rules back up, so it will be applied. Yes.
So, what if, I mean, if you have a real program and you wrote besides Fibonacci, and you've written a script for that with HERMIT so that you can optimize it, but now somebody simply adds new functionality to that program. How robust is your script?
Okay, well, it depends how you write your script. So we have some high-level combinators, and we have some very precise combinators. So it does very much depend how you define your script. I mean, we have a choice operator which says try this transformation. If it fails, then try this instead. We have transformations that will try things out, and even if they don't work, it will continue or stop as you've told it. So to give, say, a concrete example, I mentioned the append vanishes transformation previously. So we've tried that on 3 different examples of reverse, true flattening, and quick sort, and we've been able to write a single script that applies that transformation for 3 programs. So to do the transformation in the context of 3 different programs. Now, I'm not confident that will generalise to all possible append vanishes examples, but it does mean you can have a sort of general purpose script that can carry with different code. But it does depend on what high level you work at when you write it. You can write very precise code for you. Certainly, we do need to test it out to do examples, and that is what we plan to do, but we just haven't done that yet.
So does that mean you're kind of building a set of primitive transformations, like how to deal with appends, how to deal with this memoization, or
yeah, we're trying to build up a library of transformations and then try and make them modular and build up higher level more abstract strategies.
Peter?
Yeah, so I have a two-chain question. So you're dealing with core, is that external from the GHC compiler or is it internal?
So it's inside the GHC compiler. So we're just using this GHC plugins mechanism which allows us access to the core midway through compilation. So that's what our mechanism is provided by GHC now.
So you're not exporting something and doing something outside, but it's all
inside.
Related to that, does GHC have a core parser?
Core parser.
I mean, you imported, you build your own parser.
So we're just using the GHC core data type. It's already been parsed by GHC. We don't print it out or parse it, we just work on the data structure directly. I mean, we're just printing those as a view of it, but they're not.
Yeah, Tom?
Speaking of which, is your pretty printer available as a library? That's really good.
Unfortunately, I didn't write it, the other guys did. But it's not available as a library in itself yet. If people want that, I can certainly suggest it. And you can always just load up HERMIT and just view its core.
I'm certainly going to use it even if only for that.
Yeah.
Yeah, I mean, we've got several 3D printers. I have a latex 3D printer that's generating the paper as well. Yeah, we're very interested in feature requests, so if there's bits of it that people are really interested in, let us know. See what we can show.
All right. Thank you very much.